Today we are going to present our data, as sir has already announced. It is on epidemiology and treatment option for multi-drug resistant bacteria from clinical samples. So it was in way back in 1945 when the discoverer of first antibiotic, that is the penicillin, Mr. Alexander Fleming, he postulated way back in 1945 that it is not difficult to make microbe resistant to penicillin, and a time may come when penicillin can be bought by anyone in the shops. Then there is a danger that the ignorant man easily underdose himself, and by exposing his microbe to the non-lethal quantities of the drug, make them resistant. So this is around so long he postulated, and that is the reality now. So people continue to make, scientists can work very hard and continue to make antibiotics, but these bugs are much more smarter than us. And just after the discovery, within no time they find their ways, and by one means or other they develop resistance to this antibiotic. Then we try another, and they also try. So this is a battle which is going on, and the eternal battle between the bugs and the bottles continues, and nobody is ready to give up. So this is just show you the roadway of antibiotic discovery. So the first one was the penicillin, as you all know, and thereafter, in between the 1950s and 70s, lot of antibiotics came up, various group of antibiotics. I'm not going to read them, you all know. Then as we go along, we see that the graph is narrowing, that from 80s, 19 and 2000, and now we have, initially we had so many antibiotics coming up, but now we have very few antibiotics are coming up. Why? Because it is primarily because it is very difficult to, because out of thousands of molecules, you come to a very few, then there are clinical trials and others. So they say that it takes at least 20 years to develop antibiotic. And then bacteria, they take no time. So, and then there are a lot of monetary issues. So now it is not a very good, this is not a very rosy picture for the industry either. So we have very few antibiotics which are in pipeline. So we all know, but let us see again what do we mean by antimicrobial resistance. So clinically, it is unresponsiveness of infection to antimicrobial therapy with a standard dose or duration, or if we talk in microbiological terms, it is the ability of the microorganism to multiply in presence of drug concentration higher than the therapeutic doses which are usually used in the human. It is a natural phenomena. It has to happen. So it is a natural phenomena of evolution which is slow and continuous. We cannot stop it. It is bound to occur. And once developed, it is very difficult to reverse, and most of the time it is irreversible. So it has been a problem of many decades. So antimicrobial resistance is a decades of concern, and way back in 1981, WHO Scientific Working Group on the Antimicrobial Resistance reports include guidelines for the appropriate use of antibiotics. Then in 2001, WHO Global Strategy for Containment of Antimicrobial Resistance came up. In 2011, World Health Day had the theme of antimicrobial resistance, no action today, no cure tomorrow policy. This was taken up. And in 2015, adoption for the Global Action Plan for AMR came up. And in 2016, AMR resolution at the United Nations General Assembly, you can see a few of the pictures, where all the countries, they were asked to prepare a national action plan in line with the global action plan came up partly, but in 2016 all the nations, they were requested to take up a national action plan. But if we see what is the data, so if we look at the picture, this is a bit old picture because we don't have such pictures like current. So we have taken this up, and if you can see, it is a very patchy distribution, like from few countries we have data, but from most of the countries we don't have data. And we discuss about India also. So it is not only an Indian problem, but it's a global threat. And it is postulated that the resistant infection currently claim at least 50,000 lives each year across the Europe and US alone. And it is projected to cause 10 million deaths per annum by 2050, with 4.5 million deaths in African region and 4.7 million deaths due to MR in Asian countries respectively. And the cost, of course, this is a gross underestimation, because many of these are not being reported, and many of the centers, they don't do so, they cannot report either. So, and the cost, as you can see, is huge. So if we talk of Indian data, we all know that India carries one of the largest burden of drug-resistant pathogen worldwide, and we have alarming high resistance among gram-negative, both the gram-negative and gram-positive bacteria. And we don't have any pan-Indian study, but whatever the regional study which they report high MR among pathogens such as Salmonella typhi, Shigella, Pseudomonas, Acinetobacter, even Staph and others. So recently ICMR has, so this is the largest study we could come across. We can say pan-India, though this is not pan-India, but this included around 5,700, they took the sample from 5,700 collection centers nationwide, and here we can see they reported for two organisms. One is antibiotic resistance of Klebsiella pneumoniae, and another is for Staphylococcus aureus, where the resistance is very common. So these two they reported, and we can see in the left side that the resistance to, though the other groups they have stabilized, but the resistance to this carbapenems, it is steadily increasing. And if you look at the right side, that is the Staphylococcus aureus, there we can see that the resistance to other group, oxacillin, methicillin, and other groups, they came up, but now they are more or less stable, like MRSA. It is around, in our centers it is around 50%, but they have reported around 40%. It is pan-India. And then, but still we have low resistance to vancomycin and others. So this is what, but recently ICMR has come up with a study. It is from 10 different centers in India, and that results will be compared with our data in the future slides. So very briefly, antimicrobial resistance types, it is, we all know it is intrinsic, that here the person has not been exposed to antibiotic, but even then he is resistant to that. And so I have mentioned a few, the list is used, I am not going to read, but here like anaerobes, they are not susceptible to aminoglycoside. Why? Because there is no oxidative metabolism for their uptake. Similarly, metronidazole we use for anaerobes and not for aerobes. Again, why? Because they are unable to reduce the drug to their active forms. So there is a huge list of organisms and drugs to which they are inherently resistant, and we must know that. So these should not be used. Then the acquired resistance, which may be either due to the mutation or due to the acquisition of or the transfer of the genetic determinants. And here the mice increases suddenly, in contrast to the mutation where there is a slow process. So this we have already discussed. Now I don't have the time to go into the detail, but because in the future slides it will be easy for us to understand. So what are the various mechanisms of resistance? Broadly three. Either there is a decreased uptake of the drug or increased excretion of the drug, or drug is inactivated due to various enzymes, or each drug has a target where it acts, so that target itself is modified, so the drug cannot act. So this is the enzymatic inactivation is one of the important cause of drug resistance, and we have many, like for penicillin, which was the first drug, we have like it is a beta-lactam group of antibiotics. So beta-lactamases, they inactivate beta-lactam group of antibiotics. Similarly, now we have ESBL, that is extended spectrum beta-lactamases. Then for carbapenemases, we have metallo-beta-lactamases which inactivate carbapenemases, so we have carbapenemase resistance. Then we have AMC beta-lactamases, and for aminoglycoside, we have many enzymes, more than 8, which inactivate aminoglycoside group of drugs. Then enzymes mediated resistance against the beta-lactam, because this is one of the major group of drug. We have three like extended spectrum beta-lactamases, MC and carbapinamases. So these ESBLs, they hydrolyze most penicillin and cephalosporins, that is cefuroxime, third and fourth generation cephalosporins and aztreonam, but not cefamycins and carbapenems. So naturally these two groups, they may be used for ESBL, and there are a huge number of enzymes. Few of them have been mentioned. Then MC beta-lactamases, they hydrolyze penicillin, cephalosporins, including third generation, but not the fourth one, and also the monobactams. And they are poorly inhibited by the beta-lactam inhibitors, especially the clavulanic acid. Then now what we have as a last resort, the carbapenemases, they hydrolyze penicillin, ESBL, and carbapenems, and among these there are two groups. One which is having serine at the active site as a metal, and they have and another group is having zinc at the active site. And it has also, there are many subtypes. As you can see, New Delhi metallo-beta-lactamases falls in this group. Then as we talk, the uptake of drug itself is defective. So when it is not taken up properly, it cannot act. So it may be because of many reasons, like there is a reduced outer membrane permeability, which may be it may be intrinsic also, or the porin channels through which the drug enters, there may be mutation. So there's narrowing down, and the drug cannot enter properly and cannot act properly, like in case of aminoglycosides, quinolones, and also beta-lactams. Or there are, through the efflux pump, drugs comes out. So when it comes out, it cannot reach the target site and cannot again act properly, like tetracycline, fluoroquinolones, beta-lactam, and macrolides. Then finally the target modification. Each drug acts as a particular site. Some act at the cell wall, some act at cell membrane, some act as nucleic acid. So if there is a modification in the target, for example this beta-lactam, they act on the penicillin binding protein. But if the protein there is a mutation. Like instead of penicillin binding protein, there is PBP, there is a PBP2A and others. So again it cannot act. Similarly, for example, the glycopeptides like vancomycin and teicoplanin, they act on the peptidoglycans, side chains, which itself is altered. And similarly for others. So, with this brief introduction, now I'll invite our Dr. Saurabh Pal to discuss about common bacteria and their sensitivity, what is our experience. Thank you.
Good morning, everyone. I'm going to present about the SGPGI data of the susceptibility of the common organisms that was tested in the last year. It is the 2019 data. A total of 66,863 samples were processed in our lab, bacteriology, of which about half were from urine samples, the other comprised of the blood, sputum, pus, and CSF samples. Now, when we look at the culture positive samples, about 15% of the urine samples were positive, about 50% for pus and sputum samples were culture positive, and about 7% of blood and CSF samples were culture positive. Of all the culture positive samples, gram-negative organisms were attributed in 68% cases and gram-positive in 32%. Now, coming to the isolates that were obtained from blood samples, the most common isolate was coagulase-negative staphylococci, followed by, that is about 28%, followed by Klebsiella pneumoniae in 20% of the cases, and E. coli in 14% and Pseudomonas in 10% of the cases. However, among all the Staphylococcus species isolated, only 20% were Staphylococcus aureus, the rest were coagulase-negative Staphylococcus. Now, coagulase-negative Staphylococcus is the commensal of the skin and is generally regarded as a contaminated in the blood culture until unless both the blood culture bottles in a particular set comes positive. However, a significant number of the blood samples sent to our lab comprised only of a single blood culture bottle. Hence, the growth of coagulase-negative Staphylococcus in those bottles are practically uninterpretable. Hence, we have classified in these two patterns. So hopefully next year this data will not be skewed like this year. Now, coming to the common isolates from the urine, about 46% of the samples isolated were growing E. coli, followed by Klebsiella pneumoniae, that is about 18%, Enterococcus faecalis about 14%, Pseudomonas aeruginosa about 11%, and Enterococcus faecium about 4%. Of all the pulse samples, the most common isolate were E. coli in 26%, followed by Pseudomonas aeruginosa, Enterococcus faecalis, Klebsiella pneumoniae about 15, 14, and 13% respectively. Staphylococcus aureus were positive in only about 6% of the cases. Among the respiratory samples, the most common isolate were Klebsiella pneumoniae, 32%, followed by Acinetobacter baumannii, 30%, and Pseudomonas aeruginosa in 23%. Now, the Indian Council of Medical Research had formed the antimicrobial surveillance in 2012, and henceforth there are few institutions like All India Institute of Medical Science in Delhi, PGMI Chandigarh, JIPMER, AFMC Pune, CMC Vellore, Hinduja Hospitals, Hinduja Hospital Mumbai, Gangaram Hospital in Delhi, and Apollo Hospital in Chennai, and TMC in Kolkata. So these institutes have collected the various data all over India, and they have compiled up. And this data was published in 2019 by the Indian Council of Medical Research. Now, when we compare our data with the ICMR data, we can find out for Klebsiella pneumoniae, the susceptibility to amikacin in our data was only 22%, whereas the ICMR data shows about 53% of sensitivity to amikacin. As far as the carbapenem, like meropenem and imipenem, we find that meropenem was susceptible in only 20% and 25% in case of imipenem. However, the ICMR data shows about 52% and 54% respectively. Colistin susceptibility, however, was 93% in our data when compared to 92% of the ICMR data. Now, coming to E. coli, a similar reduced susceptibility can be found, where amikacin was susceptible in 48% cases, 48% in our data, and 82% in the ICMR data. Similarly, the meropenem and imipenem had a reduced susceptibility of 47 and 62% in our data when compared to 70% and 73% of the ICMR data. And like Klebsiella pneumoniae, the colistin susceptibility to E. coli was very high at 98% in both the data. Pseudomonas aeruginosa were susceptible to piperacillin tazobactam in 40% in our data, whereas compared to the ICMR it was 71%. 51% for levofloxacin as compared to 58% in ICMR data. 60% are susceptible to amikacin when compared to 69% in the ICMR data. 65% were susceptible to imipenem, which is almost similar to the ICMR data. However, the colistin susceptibility were higher in our data with 98% when compared to 92% of the ICMR data. Coming to Acinetobacter, here we can see that our data reveals a very reduced susceptibility to carbapenems of meropenem and imipenem susceptibility of 9% and 10% respectively. But also the ICMR data also suggests a reduced susceptibility at 23% and 18% similarly. Minocycline susceptibility was 79% in our data, although the ICMR data shows a reduced susceptibility of 64%. Colistin was tested in our hospital, so the colistin was susceptible in 96% of all the Acinetobacter isolates. However, the ICMR data did not provide the colistin susceptibility to Acinetobacter. Now, coming to gram-positive organisms, Staphylococcus aureus was susceptible in 30% to fluoroquinolone, where the ICMR data shows only 19% susceptibility. Clindamycin, on the other hand, was only 40% susceptible according to our data, where the ICMR data shows about 76% susceptibility. Finally, coming to vancomycin and teicoplanin, all isolates were of our data shows susceptibility to vancomycin and teicoplanin, and similar result can also be shown by the ICMR data. Coming to Enterococcus species, here we find a reduced susceptibility of only 36% to gentamicin, where the comparable ICMR data shows about 52%. The ampicillin susceptibility is 65%, where the ICMR data shows 73%. Vancomycin susceptibility was only 63% according to our data, whereas the ICMR shows about 96% susceptibility. Similarly, teicoplanin susceptibility was also reduced at 87% when compared to the I7 data. Now, I'll call upon Chima Rao, Assistant Professor, to present further.
Good morning to all of you. Now, I'm going to present the second line antibiotics. The first line antibiotics are, we put 6 to 7 antibiotics that are commonly used, like carbapenems, aminoglycosides, then third generation cephalosporins, quinolones. The commonly used antibiotics 6 to 7 these we put in our in first line data. Then, if they are resistant, then we put the second line antibiotics. Sometimes even in blood samples and sometimes in ATS blood samples, especially from critical care, we put colistin in first line also. So because the colistin is the last resort to the carbapenem resistant isolates or MDR isolates, so the colistin is very much important, not only in our center but pan-Indian or in world also. So previous year we had reported that E. coli and Pseudomonas aeruginosa were 100% resistant, 100% sensitive to colistin, but now the resistance to colistin has also been developing, and this year we found that although the colistin is now very good, still 2% resistance has been seen, and E. coli and Pseudomonas aeruginosa 98% sensitivity to colistin. Colistin is very good among towards these two organisms, and Acinetobacter baumannii 96% is sensitive to colistin. The Klebsiella pneumoniae is a proliferative organism, and we saw that around 7% resistance, that means that 93% were sensitive to colistin. And please remember that colistin is intrinsically, the organisms that are intrinsically resistant to colistin are the protease group. So if the organisms are protease, then we should not use colistin in these organisms. Now, fosfomycin is an urinary antibiotic. Is an oral drug. It is a very excellent drug for oral treatment, community-acquired UTI. It is very good drugs. FDA has also approved the use of fosfomycin for community-acquired UTI, but because now the problem of the bacterial resistance in gram-negative isolate is so much that they are also using the fosfomycin in high doses for systemic infections also. But recently, up till now, we are using fosfomycin especially for urinary isolates, and found that it is very good for community-acquired UTI because E. coli is the most common positive organism for UTI of community-acquired UTI. So 100% sensitivity we found for fosfomycin. Also, Klebsiella pneumoniae 90% were sensitive to fosfomycin, but in Pseudomonas aeruginosa around 70% were sensitive to fosfomycin. And remember that Acinetobacter is intrinsically resistant to fosfomycin. So, in Acinetobacter species, the fosfomycin should not be used. The minocycline is a tetracycline group of drugs. It is very good for gram-positive organisms also. But recently, they are using minocycline for gram-negative organisms, especially for Acinetobacter baumannii in critical care areas for hospital-acquired infections due to Acinetobacter baumannii and Pseudomonas aeruginosa, and they are finding good results. We also found that 78% of our isolates, 78% of Acinetobacter baumannii isolates, especially in respiratory samples, were sensitive to minocycline, and around 57% Pseudomonas aeruginosa were sensitive to minocycline. Also, minocycline is also advantageous is that it also can be given orally as a oral tablet. It can be given in orally. Now, linezolid is a oxazolidinone group of antibiotic. It has also very good oral options, and it mainly acts upon the gram-positive organisms, not against the gram-negative organisms, and it can be used especially in serious cases of sepsis and meningitis cases due to gram-positive organisms. But it should be reserved for the where the vancomycin or the ampicillin group does not work. It can be used in place of vancomycin. So we tested on MRSA isolates, this methicillin resistant Staph aureus, because in MRSA cases, no beta-lactam antibiotics can be given. Only vancomycin can be given, but vancomycin can be given only IV routes. So linezolid is a very good oral option against MRSA cases, and we found that 100% sensitivity towards linezolid of MRSA isolates. Also, vancomycin resistant enterococci also 96% are sensitive to linezolid. Now, T-cycline is a systemic used antibiotic. It also comes under group of the tetracycline group, and it has very good activity both against both the gram-negative and gram-positives. And especially in MDR gram-negative cases, T-cycline can be used for skin and soft tissue infection, purulent infections, and also for respiratory isolates. And it is not recommended for sepsis cases because blood level is very much low, and sepsis cases and meningitis cases it should not be used, but other cases, purulent cases, it can be used. And we found that E. coli 97% were sensitive to T-cycline. Among the Acinetobacter 87% and Klebsiella pneumoniae 84% were sensitive to T-cycline. And please remember that T-cycline, Pseudomonas aeruginosa is inherently resistant to T-cycline. So in Pseudomonas cases, T-cycline should not be used. And it recommended that T-cycline should not be used as a single drug. It should be combined with other carbapenems or colistin. So what are the we found that throughout the years, what are the trend of the MDR organisms? What are the whether it is rising or falling or it is becoming stable? We found that in 2016, the Klebsiella pneumoniae, colistin-resistant Klebsiella pneumoniae were 7%. It rose to 10% in 2018, but this year we found that it has been fallen to 7%. So around 7 to 10% we are seeing this colistin-resistant Klebsiella. MRSA isolates, they are becoming stable or slightly decreasing also. In 2010, 55%, but now slightly decreasing to around, we can say around 50% of our isolates are MRSA. The carbapenem-resistant Acinetobacter is very much problematic. The carbapenem resistance in Acinetobacter has risen to more than 90% throughout the years. Also, as we have shown, the ICMR data has also shown around 70 to 80% resistance to carbapenems also. But the isolation of the Acinetobacter should be interpreted with caution because Acinetobacter is an environmental pathogen. So, it should the culture positivity should always be correlated with the clinical conditions, whether it is a contaminant or any pathogen. VRE vancomycin resistant enterococcus has gradually risen to 15 to 17%. Now this year also the prevalence was 17%, especially in urinary isolates and purulent isolates. We are seeing this vancomycin resistant enterococcus. Carbapenem resistant Pseudomonas aeruginosa more or less risen was now stable around 50% of the Pseudomonas aeruginosa cases were resistant to carbapenems. So in this scenario, the various literature they suggest the treatment options for these MDR organisms, multi-drug resistance organisms. They have suggested that if the organism is susceptible to beta-lactams, then the beta-lactam can be used like azithromycin and ceftazidime. Even the newer beta-lactam inhibitor like ceftazidime, avibactam can be used as a backbone of the therapy, but should be always combined with other antibiotics like other second-line antibiotics like colistin or tetracycline or fosfomycin or aminoglycoside if they are sensitive. And if the backbone drug, the first-line drug is moderately sensitive, then add two accompanying drugs should be added. Then they are suggesting that if registered to the organism, is registered to all beta-lactam drugs, including the meropenem MRC more than 8 microgram per ml, but it's sensitive to at least two other drugs, second-line drugs, including colistin, then the main drug will become colistin, and other second-line antibiotics like tetracycline, aminoglycoside, or fosfomycin can be added to colistin. And remember that please, the colistin monotherapy is avoided because the resistance development to colistin if used singly is very much high. So colistin should always be combined with other second-line antibiotics. That if the organism is resistant to all beta-lactam drugs, including colistin, but it is susceptible to other drugs, then the backbone drug will become tetracycline or aminoglycoside, and accompanying drug will become either fosfomycin or aminoglycoside or tetracycline. And for systemic use, the fosfomycin should be given IV high doses. The usual dose for UTI is 3 gram single dose, but for systemic use, maximum 24 gram can be given in a single day for sepsis cases and meningitis cases also. If the organism is pen drug resistant and no susceptibility is seen or susceptible to single drug, then ceftazidime avibactam plus aztreonam can be given, because the ceftazidime avibactam inhibits all the beta-lactamase enzymes except beta-lactamase. But if we add aztreonam, that the aztreonam is resistant to beta-lactamase, then both the combination can use against all the enzyme producing bacteria. Or some are using also meropenem plus atrapenem, because they are saying that the beta-lactamase enzymes can destroy one beta-lactams, but the other beta-lactam can be active. So even the double carbapenem they are using, and they are recommending that even consider active investigational drug if available, and also test combination of antibiotics per synergy, because individual antibiotics may not work, but both combination and combinations of the antibiotics may work in this scenario. Now I am inviting Dr. Asutosh to present our molecular epidemiology of the cases.
Good morning. As the previous speakers have discussed that colistin is the last resort antibiotic for treatment of gram-negative infections, and there is the consistent rise in the resistance against colistin. So it becomes very important to understand what is the mechanism which is underlying the development of colistin resistance among the gram-negative bacteria. And I'll be discussing some of the studies that we have conducted. First, to understand colistin resistance, colistin, also known as polymyxin E, it is one of the most effective drug in case of multi-drug resistant gram-negative bacterial infections, and it is basically a polycationic antimicrobial peptide. As I said, it is currently used as a last-line drug for treatment of severe bacterial infections. In case of colistin resistance, most of the mechanisms are directed against the modification of the lipid moiety of lipopolysaccharides. Can I have some water? Send me a bag. Sorry. Yes, most of the mechanisms are directed against the modifications of the lipid moiety that is present in the lipopolysaccharide layers. And this modification in the LPS, it actually reduces the binding capacity to polymyxins, which ultimately leads to development of resistance. Most of the mechanisms studied till few years back, they focused only on the intrinsic resistance which was present in the gram-negative bacteria. But recently, a new mechanism has emerged, and it is disseminating at a very rapid pace. And this includes the evolution of a transmissible colistin resistance gene, which is known as MCR1. And this mechanism is basically plasmid mediated, and it was first of all reported in case of E. coli isolates from animals and human samples, and it is basically transmissible. It was reported in China. In certain E. coli, MCR1 gene has also been found to be integrated, and it has stabilized in chromosomes. MCR1 protein is basically a member of the phosphoethanolamine transferase enzyme family, and it leads to addition of phosphoethanolamine to lipidae which results in the LPS being more cationic. And this more cationic LPS actually cannot bind the colistin. This is the global distribution of MCR1 gene. And it is important to note that till date the presence of MCR gene has been reported in various genera, but most of them are Enterobacters. It has been reported from these countries which are represented in blue are actually the countries where MCR1 gene has been reported from different samples, from humans, animals, as well as from the environmental samples. Our center has for the first time reported the presence of MCR gene in India, and it was from a clinical sample. So the major objectives of our study were to investigate the presence of MCR gene in gram-negative clinical isolates and also to understand the mechanism of dissemination of MCR gene. We collected around 1,000 non-repeat gram-negative isolates from different clinical samples like blood, pus, and urine, and we identified them using our automated system. Then we studied their antimicrobial susceptibility profiles according to the global guidelines. We performed the sequencing of the genes with MCR1 gene along with the genes which are responsible for carbapenem resistance like NDM, KPC, and OXA48. We try to understand like what all clones are actually circulating among the patients in our hospital. So we performed the clonal lineage profiling of the MCR1 positive isolates using pulse field gel electrophoresis. We assessed the transmissibility of MCR1 gene in case of our isolates, and also we determined what is the location of the MCR1 gene in the genomes of the isolates that we have studied. Results. So out of those 1,000 gram-negative isolates which were collected, 40 isolates were found to be colistin resistant based on their AST profiles. And the distribution of those 40 isolates were, we had Klebsiella pneumoniae, Pseudomonas aeruginosa, Providentia redgeri, Myroids species, Serratia maxens, and Stenotrophomonas maltophilia. Those 40 isolates, then we screened for the presence of MCR1 gene using PCR and Sanger sequencing, and we found that out of the 40 isolates, 12 isolates actually harbored the MCR1 gene. And the isolates in which the MCR1 gene was present were Pseudomonas, Klebsiella pneumoniae, Pseudomonas aeruginosa, Providentia redgeri, and Myroids odorectus. So we then submitted all those sequences into the global NCBI GenBank database and decided to proceed with the Klebsiella pneumoniae isolates and the Pseudomonas aeruginosa isolates for further characterization. So we included one isolate from Enterobacter and one from non-Enterobacter gram-negative. We performed the, along with the screening of the MCR1 gene, we also screened the presence of carbapenemases in the Klebsiella pneumoniae isolates by sequencing. And special focus was on KPC, OXA48, and NDM gene. And we found that all the 4 Klebsiella pneumoniae colistin resistant isolates were negative for the carbapenemase genes KPC and OXA48. But in one of the isolate, NDM was found to coexist with MCR1 gene. This is the AST profile of the colistin-resistant Klebsiella pneumoniae isolates, and as you can see that all the MCR1 positive isolates were resistant to carbapenems, third generation cephalosporins, aminoglycosides, and ciprofloxacin, but they were sensitive to tigecycline. Then we tried to understand as to what kind of clones are actually colistin-resistant clones are actually circulating among the patients who are coming to our center. So for that we performed the clonal lineage profiling of the 4 Klebsiella pneumoniae isolates by pulse field gel electrophoresis. This picture actually shows the PFG gel, and 3 isolates, this lane 3, 4, and 5. Three of the isolates were showing a similar banding pattern. That means they were clonally related to each other, and one of the isolate was different. And it is important to point out that the 3 clonally related isolates were actually coming from different clinical samples, and they were coming from different wards. So this might be a dominant clone which is circulating among different wards. Then we performed the screening of carbapenemesis in Pseudomonas aeruginosa isolates also. And here also we found that the 4 colistin-resistant Pseudomonas aeruginosa isolates were actually negative for carbapenemes genes KPC and OXA48. And again, we found NDM to coexist with MCR1 gene in one of the isolates. This is the AST profile of Pseudomonas aeruginosa isolates, and we found that all the MCR1 positive isolates were resistant to carbapenems, 3rd generation cephalosporins, aminoglycosides, and ciprofloxacin. We performed the clonal lineage profiling of Pseudomonas aeruginosa isolates also, and this picture shows that one of the colistin-resistant Pseudomonas aeruginosa isolate was different, while 3 isolates were similar to each other. That means they were clonally related. And again, all these 3 similar clones were coming from different clinical samples and from different wards. Since MCR1 gene is transmitting at a very high pace, so it becomes important to assess whether it is transmissible or not in case of our isolates. So we performed the transmissibility assessment of MCR1 gene in Klebsiella as well as Pseudomonas aeruginosa isolates by performing the conjugation experiments. And we found that our experiments did not yield any transconjugates. So we inferred that MCR1 gene was either present on a non-transmissible plasmid, or it may be present at some other genomic location in the Klebsiella as well as the Pseudomonas aeruginosa isolates. Since we did not get any transconjugates, so we decided to find out as to what is the genomic location of MCR1 gene in case of the Klebsiella genome. And we performed, first of all, we performed the pulse field gel electrophoresis and later the southern hybridization using MCR1 gene as the probe. And we found that the MCR1 gene was located on chromosome in case of the Klebsiella pneumoniae isolates. So the gene has actually integrated as well as stabilized on the chromosome. Similarly, we performed the gene localization analysis of MCR1 in case of Pseudomonas aeruginosa isolates also, and here also we found that the MCR1 gene was located on chromosome in case of Pseudomonas isolates. Recently, we have started screening for MCR1 gene in case of Acinetobacter baumannii. So we collected a total of 40 carbapenem-resistant Acinetobacter baumannii isolates. And based on the AST profile, we found that 11 isolates were actually resistant to colistin. We screened these 11 isolates for the presence of MCR1 to 4 gene. And actually, there are now several variants of MCR1 gene that have evolved. And it is MCR1 to 10 now. But initially, we have screened for MCR1 to 4 gene by PCR. And when we performed the Sanger sequencing, we found that the MCR1 gene was present in 3 of the isolates, and a variant of MCR1, MCR3, is present in 2 of the isolates. We screened for the presence of carbapenemesis also to find out whether they coexist with MCR1 and focused on NDM and OXA48. We performed PCR and Sanger sequencing, and we found that both the genes coexisted with MCR1 gene in one of the isolate. But these genes were absent in the isolates harboring MCR3 genes. So we have a Acinetobacter isolate where OXA48, NDM, as well as MCR, all 3 genes are coexisting. We are currently screening for MCR4 to MCR10 genes in the isolates, as well as the genes which are imparting the intrinsic resistance in case of Acinetobacter. So the significance of this work was that we have for the first time reported the emergence of MCR gene in Klebsiella pneumoniae as well as in Pseudomonas aeruginosa isolates from India, and presence of MCR3 and MCR1 in Acinetobacter is the first global report. The gene has been integrated and stabilized on the chromosomal DNA in case of Klebsiella as well as Pseudomonas genome. So it is important to mention that the co-occurrence of MCR1 with NDM or with Oxa in Klebsiella, Pseudomonas as well as Acinetobacter isolate, it indicates that we are actually leading towards a situation where there might not be any options available against the infections caused by such organisms. So I invite Professor Ghoshal to sum up the presentation.
Thank you. So, as we saw, antibiotic resistance is a problem of concern, especially in gram-negative bacteria. Many bacteria are sensitive only to few antibiotics like colistin, tigecycline, fosfomycin, and even resistance mechanism to these antibiotics, they are increasing or developing. So, optimum use of current antibiotics is essential, and culture-directed antibiotic therapy, it is a very important step, and it is very important to check the antibiotic resistance that we give. We do culture and find out the sensitivity and give antibiotic accordingly. And these 5D, they are called the essence of antimicrobial therapy. That is the right diagnosis. We have to diagnose it correctly by using appropriate methods, which we are trying. Then the right drug at the right dose and for the right duration. All these are important. Dose and duration. Suboptimal therapy should not be given. And then as soon as the culture, even if many times you have to give empirical therapy, but as soon as the culture therapy, the culture results come, sensitivity report comes, de-escalation, proper de-escalation is very important. So please remember 5Ds. And also it is very important to remember that you have to treat the infection, because we have bacteria or the microbiome all along in whole various sites of our body. So we have to treat the infection and not the colonization. For example, we have to treat the pneumonia and not the tracheal aspirate, because many times we get the organism from there, but it has to be, there has to be quantification, there has to be clinical correlation. Patient has to be seen what antibiotics he is on, his immune status, many things need to check up. We need to check. Similarly, treat urinary tract infection and not only the catheters or the simple bacteriuria, because urine itself is a very good culture media if we get it after a long time, or if it has been kept for some time, and then after we culture it, then whatever is said that the more than 10 to the power 5, that will not be proper, because it will give false high results. So we have to take all this into the consideration. Similarly, treat the bacteremia and not the catheter tape of the hub. Similarly, we don't have to treat like Dr. Chinmay told you that we are getting around more than 22. Most common isolate in our blood is Staphylococcus, coagulase negative staph. So we are not in a position to say whether this is causing infection or this is a skin flora, unless we have two samples from two different sites and these have been taken at two different points of time, right? So, therefore, for prevention of resistant bacterial infection, it is one person cannot do it. It is a multidisciplinary approach. So, proper lab detection, there has to be proper lab detection and reporting. Then proper hand washing, as we see, regularly emphasize, because when you all are busy clinician, and when you go from one patient to another, these various studies have shown that from one patient, if you touch another patient, and these may be easily transmitted unless you wash hand or using any alcohol rub or that sort of thing. So proper hand washing. Then educational activities like staff, we all keep on reading, but our nursing staff, our other staff, those who are in contact with the patient, take their samples, they also need to know. So they have to be educated. And then at the earliest point, we have to turn off the unnecessary antibiotic uses. And this is like questionable whether the cyclic use of antibiotics, in many cases it helps. Like chloramphenicol, earlier it was stopped because of various side effects. Now again it is showing good results. Similarly, trimethoprim, sulfamethoxazole, methoxazole, it has been seen that when you stop any antibiotic for some time, then it again becomes sensitive. So similar things. So thank you, and if there are any questions, we'll be happy to answer.